Okay, Chemistry 125, we are back. This is part 2 of the two-part experiment with iron ACAC3 or iron 3 acetylacetonate. So we're going to isolate it today. That's the idea, is to purify it a bit, but then also to check its purity using melting point. Melting point is very good as an indicator for purity. I believe you've been given the melting point of the compound in the procedure. We're going to do some other stuff. So when you come in, it's very important that you get the filtration, the vacuum filtration apparatus set up and your product filtering as quickly as you can so that it can sit there and dry till it's a very fine powder. I believe we've described it like a fine red sand. So it's not sticky at all, it's very powdery, it's obviously very dry, all the moisture has been driven off. That is one of the major sources of error here, is not letting things dry properly is a big one. Okay, so I'm going to come out and do that. There's some pre-lab questions here, but I think I'll just explain them when I come out in front of the video. So let's get started. Okay, so this is not the exact title of the lab. That's mine. I think we're calling it Isolation and Characterization of a Solid Product. So make sure you print this out and read through it. I'm not going to go through every little detail. Oh yes, the accepted melting point of the product is 180 degrees Celsius. So you know what that's supposed to be if it's pure. And we'll go into that later. So in terms of your pre-lab questions, if you have to go back and redo the theoretical yield, again, that should be the number of grams in a perfect world, a perfect experiment. It's a complete reaction, 100% efficiency transferring from one container to another. Perfect, never happens. So that should be your theoretical yield, and that should be in grams. Another couple of questions here is calculate the percent yield, and I think the percent yield calculation's been shown somewhere. Okay, if not, percent yield's pretty easy. It's what you got in the lab, your experimental yield, divided by your theoretical yield times 100. It is not the same thing as percent error. In fact, I tacked this on as a third question, because this comes up so much. Is students confusing percent yield, when do you use it and why, and percent error, when do you use it and why? So I'd like you to explain the difference between those two calculations, percent yield, percent error, when you use them and why. Very important. And question 2, going a little bit out of order here. So I have 3 sets of data, well, just numbers I made up. 3 experimental yields from the experiment, is calculate the percent yield for these 3, and then kind of speculate a little bit on what would have gone, like which one's the best one. Well, why is that? If you have a really high percent error or high percent yield, or a percent yield that doesn't make any sense, what would explain that? An extremely low percent yield, well, you can see which one that'll be probably, is what makes sense there. So that's sort of a warm-up for writing your conclusions. And these are just some of the pre-lab questions that your instructor may give you. Okay, so racing forward into the lab. You want to come into the lab and set up the filtration apparatus immediately and get your product filtering, which is the first thing I'm going to show you. It doesn't matter how long that goes. You want to let it go until, I think I already said it on the video, until it's almost like a fine red sand, if my memory is serving me correctly. That's what you want to see. Okay, let's go. And then I'll show you the second experiment. So quickly, so if you only have time to watch the first part of the video, not the second, that's okay. Actually, it's not okay, you should watch the whole video. So vacuum filtration. So let's see, I'm jumping to the procedure, set up the filtration apparatus as described. Okay, I've got all the stuff here. So let me get that out of the way. So we want to, here's the filter flask. The Hirsch funnel and adapter goes on top of that. This one fits pretty tightly. It's very important that you get a piece of filter paper that fits right over the holes in the funnel, that it's not sitting on the sides flat and it's covering all the holes. Most of you have this size, some of you will have a different size, and I think these little pieces of paper, and you want to make sure you just get one of these. They have a tendency to stack on each other. You only want one. In fact, there's 2 of them here. Yep, you just want one. That should go over the top. Actually, this is not part of the procedure, but you may want to weigh this. If you record the, because eventually you're going to scrape the solid out onto a watch glass and let it all dry, and this is going to have your product all over it, and you'll want to pull it out and throw it away. But it might not be a bad idea to weigh this, so that when you weigh everything, you can just subtract off the mass of the empty filter paper. You don't have to do that, but it can be helpful. It's not part of the exact procedure, but it's a little tip. Okay, so the filter paper is in here, filter flask, adapter, here's your tubing. The order that you do this in might be a little different, but when you put this tubing on here, this is heavy tubing. Make sure there aren't any cracks in it at the ends or anywhere in the middle. If there are, the vacuum won't work. You want to clamp this. I mean, you really want to get a clamp on there so it doesn't fall over. This tubing will make it tip over. So I'm going to disassemble this and clamp this. Here's a ring stand. The 3-prong clamp should fit around there. Yeah, that fits okay. Barely, but it's okay. You may have a bigger clamp in your drawer, which is fine. So there's the clamp itself. Here's what holds it onto the ring stand and the actual clamp. So one side, doesn't really matter which one. This is a symmetric, believe it or not. So slide it in one side, clamp it down. We'll make some adjustments later. Get that going. Okay. Sorry, it's not very exciting to watch me do this, so I'm just clamping down to make sure it's all secure. This isn't going to fall out. Just test it before you assemble everything. And it's really best, I don't know the best way to show you this, is you don't want this suspended in midair like that in case it slips for some reason. So let's put this as close as you can. That should be fine. Maybe I'll lower it a little bit more. That's tight, those are tight. This is nice and secure now, that's not going anywhere. And your vacuum is going to be over on the side. Make sure, I think the original version of this said hook it up to the gas. Okay, you don't want that, I'm sure we cleaned that up. So you've got gas, air, and vacuum. You want vacuum. So hook that up to one, and we hook this up to the other one. It doesn't have to be cranked on there. And that should work pretty well. Let's just test, make sure it's, I don't know if you can hear that. Air's not being sucked down. Air's actually being pushed down from the atmosphere. The vacuum pump creates a lower pressure on the other side, and therefore atmospheric pressure is now pushing down through. And yep, that works pretty well. Listen, I don't know if you hear that. That was the suction, okay, pushing down on my hand. Okay, so that works. Let's make sure it works when we put the funnel on. Put the funnel on. This fits very tightly. Lost my paper. Turn it back on again. Now, the paper is covering the holes, so you may not hear the vacuum now. It's kind of interesting, you don't hear it anymore. But, oh, it's still working. I think the fact that it's coming through those little holes now, it's a little bit stronger. So that actually is held on there very tightly because of the vacuum pressure. I'm just going to let that sit there. That's okay. Now, your instructor may have some small variations on how they expect you to do vacuum filtration, but this now apparatus is ready to go. And let's assume now that you've gone, I don't have a product here. This is your product from last week. If you use your imagination, it's going to look probably deep red, I think, and there hopefully is a bunch of solid covering the bottom. Again, write down your observations. I know you wrote this down last week, but write it down again. Maybe something changed. Maybe all that stuff you wrote down last week, now you look at it and it turned purple. Something's wrong then. Or it turned some other color, or something happened. So if you don't have observations, then you won't have it. So take off the parafilm, and now you're ready to filter. Couple little tricks, again, your instructor may have suggestions on the best way to do this, is the filter paper works really well if it's been wetted a little bit, so it sticks to the bottom, adheres is a better word. So just a little bit of water, just a little, and that'll form a better seal. So when you pour the solid in, it doesn't go under the filter paper and down into this flask. So again, I'm only going through the motions here. So what you want to get all of this heterogeneous mixture poured over the top so that the solid collects, and that's the precipitate or the solid. What comes through is called the filtrate. In this case, the solid is our product, the filtrate is our waste. Important to know the difference so you don't throw away the solid and keep the liquid. So the solid is what you want, as obvious as that sounds. Okay, so you pour this out, then you want to get every little bit of this out there. I don't have any great ways to demonstrate this for you. This is your rubber policeman, the laboratory version of a rubber spatula. You can reach in there, scrape the sides, get it out, get another spatula, scrape it off, back and forth. The spatula itself might actually be better to get every little bit out. And this is going to be messy. This is going to be solid all over the place, but hopefully now the filtrate has come out and you start to see some solid on there. To get more of this out, a couple things. The procedure says you can rinse with deionized water. Now again, that's fine. You could measure that. You could take some deionized water and kind of minimal. Squirt the sides, get more, and then swirl it around and dump it out, a little bit more, swirl it around. That actually does a couple things. It helps wash the solid out of here, and it helps to dissolve any impurities that are soluble in water, of course, out of your solid. So for example, if you look at your solid observations, write that down, and you see little other colors in there that don't look like everything else, that might be washed away by taking a little bit of deionized water and rinsing it over the top. Again, minimal. Don't add so much that you're filling up this flask. Just minimal amounts of water. That's fine. That's vacuum filtration. I don't think I have anything different there. Allow the solid to dry in the filter funnel for 5 minutes as air is being drawn. Okay, it says 5 minutes, but it might take more than that. So what I would do, the procedure is just fine. I would let that dry. You're not going to hurt it. If you dry it for 15 minutes, you don't destroy it. It's not air sensitive. It's not that air sensitive. So let that go. You can have that somewhere where you're not going to bump into it, and you can get ready for the next step. Okay. Yeah, the melting point apparatus. There's a great diagram in the lab manual. It's really tremendous. It's actually better than what I can show you here. So I'm going to kind of talk through this, and I'm just going to show you one example. The procedure has you record melting points for all 3 solids at the same time, which is great. And you know what? I should have added this up here. Another Prelab question. You're given the melting point for iron 3 chloride, or excuse me, iron 3 agac as 180 degrees. So find the melting point of the 2 solid reactants. So you've got iron 3 chloride hexahydrate. The hexahydrate is crucial, not just for molar mass, but for melting point. And find the melting point of sodium acetate trihydrate. Again, trihydrate. If you look up the anhydrous without water, it'll be a much different value. And they're pretty low. These are very low melting points compared to iron 3 agac. So you have 3 melting points, so you know what to compare them to. Okay, let me show you how to set this up. I'm just reading the procedure. For each solid, tap open. Okay, I'm just going to show this. This is a melting point apparatus. It's a great diagram, great photograph, I think, that Dr. Kegeris took. So when you get one of these, make sure it's dialed to 0 and that it's off. So the open circle is off, the closed lines is like binary codes. 0 is off, 1 is, or slash is on or 1. So make sure that's off. Okay. and then plug it in. You always plug something in after you're sure all the dials are off. Okay. Some basics here. There's again, the picture's better. So there's a thermometer which looks like this. It's a solid state thermometer. It's a good idea to turn this on. It's battery power, so turn it off when you're not using it. And just kind of look at the temperature, make sure it's reading something logical. And what's room temperature? In Celsius. Well, it's about 20-ish degrees. So this is reading 20, good. Turn that off since I don't need it right now. And that goes right there. Great. So now we have to get samples, 3 samples, 2 solid products, and then your product into here. That's actually kind of difficult. And I'm just going to show you for one example how to do this. So there'll be these capillary tubes. Well, I think you'll see it. I'm just going to come down here to make the point. So this is a capillary. This is a thin glass tube. It's closed, sealed on the bottom end, and it's open on the top end. So what we're going to do is take some solid, take the top end, and tap it on the solid to get some to stick in here. Then we're going to turn it around and tap it on the closed end to get that solid to come down into the bottom. The key is you only need a couple of millimeters of solid down here at the bottom. More is not better. Just a little bit of sample down at the bottom of the capillary tube, and if some other gets stuck up in the top part, like you can't get it all to go down, that's fine. Just want a little bit down here. How do you do that? How do you do that 3 times? Okay, I'm not demonstrating the iron 3 chloride hexahydrate. That stuff is a mess. So when you get that sample prepared, you want to prepare it quickly. Get it into the bottom here quickly, or else it'll absorb that water in the air and just get all messed up. So when you do the iron 3 chloride hexahydrate, put a very small amount on the watch glass and prepare the sample quickly. Tap it, okay, but I'm going to show you within the sample, I don't have to move so fast. Okay, you keep saying okay a lot, I gotta stop that. The sodium acetate trihydrate is a little hydroscopic, and I'm just going to take some and put it on a watch glass. It's probably best to have 3 watch glasses, or do this for 2 of them and clean it for the 3rd one. I'm going to bring this out. So I just made a mess, so be a little more careful than that. These crystals are pretty big, but I'm going to see if it works. So take the open end, kind of tap it on there, and that's not working too well. Well, no, it's fine. I'll try to hold that out. There's a little bit in the top where I just tapped it. Now I want to tap it on the bench so it goes down here. See, just be careful you don't break it. Actually, these are not that fragile. If you hit it straight up and down. Well, okay, that worked a lot better than I thought it would. I was going to have to show you some other stuff. So I have a few millimeters down here at the bottom that have collected the bottom, and there's a little bit at the top. Don't obsess about getting every little bit down at the bottom. Please don't do that. And don't worry about taking this solid that's left here and putting it back in the container. We'll just throw that away. I put out way too much. All you need for the cat is like a spatula tip full to get into here. I distributed way too much. That's very wasteful what I just did. I do want to show you this though. If you're getting frustrated and you can't get any of the solid to go down in here, here's an option for you. And we have a whole bunch of these in the closet after the 3rd fume hood. So after the first 3, before the last 2, there's a closet, and it has a bunch of these glass tubes. You can actually put, it's just a tube, I don't know if you can see that, open on both ends. You can drop the capillary in the top and drop it and let it bounce, and that will pack that solid down. You can do that and then pull it out the bottom. I'll do it one more time because it's fun to do. Can you hear that bouncing? Wait. That packs it in very nicely. Okay, fine. So you've prepared all three samples. You've got the sodium acetate trihydrate, you've got the iron 3-chloride hexahydrate, again, which is a mess, maybe wear gloves, and you've got some of your solid product here, which we're going to go cycle back and talk about that. So, how do you do this? So, there's a chamber in here that has 3, what's that? Vertical? Yeah, vertical slots. So you should be able to fit 3 of these in. So I'm going to go left to right. I'm going to put the iron 3-chloride hexahydrate in the first chamber. I'm going to put this in the second chamber, and then my product in the third chamber. I actually recommend making a diagram in your laboratory notebook so you know which chamber has which. It should be obvious. One's white, one's kind of gold, and one's red, but you know, make a diagram. So I'm going to put this in the second chamber, I think. Yeah, there we go. You won't be able to see it. I think I missed it. It goes in the middle chamber. I think I got it this time. All right, so you're ready to go. Your 3 samples are in. Turn it, make sure it's turned down to 0. If you have it cranked up already, it's going to heat up way too fast and you'll miss the melting points. So turn it on. I'm just going to kind of sort of illustrate this. It's easier to do it than to explain it because you can't see everything. Okay, so turn your thermometer on. Make sure it's reading something properly. If the batteries die on you, well, that's actually not a big deal because you can take the samples out. If they've already melted, hold them out in the middle of the air, let them re-solidify, and just do the experiment again. You don't ruin it's just melting. It's a physical change, remember. So it's not like we're burning the chemicals. Well, I shouldn't put burning in quotes. All you're doing is melting them, and then it can solidify, it can freeze later. So here's the trick with the melting. You have this on, turn the dial slowly. Well, not slowly, turn it up to a small, like maybe up to 2 or 3. You want the temperature here to change gradually. And you should, as part of your Prelab, you should know the melting points of all 3 things. Little hint, one of the melting points is really low, one's sort of low, and your product is really high. So you may have to crank it up a little bit to get to your product. Here's the key. So you know your 3 targets. You know when about they should melt. Okay, so you'll look through this little pane of glass, and there's a lens in here. So it's like a microscope. It's not as good as a microscope. And you'll see all 3 samples lined up. I'm not going to make a picture. You'll see it. And you'll see the individual crystals. It's very interesting. How do you record the data? Well, you have to pay attention to where you are, where the known ones are. Watch it, and as the temperature approaches your first melting point, pay very close attention because you'll see a crystal, boom, it'll sort of turn into a liquid, like pop. It won't make a sound, of course, but one crystal will turn into a liquid. Record that temperature. When all of the crystals have become liquid, record that temperature. You actually want to record the temperature, melting point temperature range, not just one temperature. Where does it start? Where does it stop? And the melting point, which is how they're reported, is the average of the first and the second. The melting point range is also an indication of purity. If something melts over a very narrow range, it's pure. If it's a very long range, like say it melts over 10 degrees, highly unlikely that it will do that, then it has a lot of impurities in it. And that may go for one of our reactants, hopefully not. Okay, so there I am saying okay again. So you have the temperature rising gradually. You see your first melting point range. If you need to, if the temperature levels off, you have to turn it up slightly to go to the second melting point, and you may have to turn it up significantly to get to your last melting point. So you want to record all 3 melting points. Your two solid reactants. Wouldn't make sense to do acetylacetonate, it's already a liquid. And then your product. And I think that's it. When you're done, disposal of waste will be in 2 separate locations, I believe. And that should be it. Everything else we should be able to mention in the lab. Oh, I brought this out in case. This is just an add-on. If you have one of your solids, not iron 3-chloride hexahydrate, that's going to make a mess in here. If you need to pulverize it a little, like smash it up into a powder, we can use a mortar and pestle. I don't think we're going to need to do that. Of course, you wouldn't do it holding it up. You'd put this on a bench and then push down and turn. Oh, this is the mortar, this is the pestle. I think that's the way it goes. I always get this confused. No, this is the mortar, this is the pestle. Mortar, pestle, yeah. We probably don't need that. And that should be it. Again, observations, observations, observations. Your product should look pure. It shouldn't have any impurities in it, like little flecks of other color or anything like that. But make sure you write down all that. This has to be totally dry. So once this is dry, what you can do is even take a clean spatula and move it around. And if it's really dry, but if it's sticking to the spatula, well, then get another spatula or whatever and scrape it back and keep all that in there. Maximize your yield. And we should be good to go, folks. That's it. I don't think I'm missing anything. It's a good 1-2 lab. So we will see you in lab, and your instructor may have some more pre-lab questions than this, but that'll be a good place to get started. Take care. And we are out in 3, 2, 1. Bye-bye.